So first of all, thank you everybody for being here and for taking some time out to get ready for tomorrow's test. So I wanted to draw your attention to a couple things before I took your questions. First and kind of foremost here, I wanted to address the sample test that I gave you did not have thermochemistry questions in it because that was not a topic of focus in previous semesters. And so that's why I gave you this packet here, just so that you can kind of see. Hopefully you've been studying thermochem kind of out of your quizzes and homework assignments and whatnot. But this is a group of about 13 sample test questions related to thermochemistry. And I have a couple of extra copies here if you want to take them to somebody else that isn't here. They're also in, I just added them to Blackboard here as well. So if you want to access them again, or if you want to look at it digitally because you're studying on your computer, it's there. The other thing that I wanted to address, and I addressed this in the video, which hopefully you watched, I just want to kind of make sure that we are on the same page as far as what this exam is. So we are going to be taking what is called the 2018 General Chemistry exam for first term. That exam is an exam that is generated by the American Chemical Society. So it is taken by chemistry majors all over the country, and actually in several U.S. territories as well. Anywhere where the American Chemical Society has a footprint, this is one of the primary exams taken by those. And the topical list is right here. And what you can see, or what you should see out of this list, is that there really isn't a whole lot of anything that is unfamiliar to us. So the primary 8 topics that are listed here are ones that we've definitely seen throughout the semester. So we've talked about chemical formulas and nomenclature. We've talked about atoms and isotopes. We've talked about all the different types of chemical reactions. We've talked about stoichiometry and mole calculations and solutions. We've talked about thermochemistry. We've talked about the quantum model. That was the 3rd chapter that we did, 3rd module. We talked about bonding and molecular properties. That's stuff that we've done in the past month. And we just finished up last week our unit on gases. So there's nothing in this list that you haven't seen before. Now, the key on this is depth. The exam itself is designed to go after a variety of concepts within those big subcategories. And there are questions in there that are deliberately difficult to try to kind of help to figure out who knows more and who knows less. So there are some definite questions in there that go above and beyond what most would consider standard knowledge for a general chemistry. It's in the same realm, but it might be a little bit more sophisticated of a problem. It might require a little bit more of kind of creative thinking to get to what equation I need to use. Speaking of equations, the exam itself has within it a periodic table. Inside of the exam booklet itself, there is also a list of constants, and there are a few relevant equations that you're given as well. In addition to those, we will also be providing you the normal equation sheet that we've given you on every exam, every quiz, and we'll also be providing you with those Vesper hybridization tables that you used in the VSEPR modules. So those will all be available to you. That's not standard fare for an ACS exam, but we feel that it is a fair interpretation based on what we've asked you to memorize and know how to do all year long. So that disqualifies us from submitting our work to the ACS, but that's kind of okay. Just as a, I talked about this in the video as well, this is a norming page. This tells us there were over 9,770 students that took the exam during the testing period for this. This test debuted in 2018, so it's roughly 5 years old. During their administrative time, nearly 10,000 students took the exam from 38 different institutions. And the representation there, some of those were big schools, some of them were small schools, some were public, some were private. The thing that all of these students had in common is that they were all in General Chemistry 1, just like you are. And what's important for us to know out of this are the statistics here. So, how many of you are familiar with percentiles? Okay. So the concept of a percentile is kind of this. Let's say that you're comparing yourself to 99 other people. So you plus those 99 people made up 100 people. And those other 99 people represented kind of the totality of all of the different scores that could exist. The percentile would be how many of those 99 students you competed and did better than. So the median score, 41, is the 51st, in this case, percentile. That's pretty much right smack dab in the middle. Half of the students did better than you, half of the students did worse than you. And as far as like scoring goes, that's what we would consider kind of about the middle as well. We would expect half of you to score somewhere around 40, 41 out of 70 on this, and the other half to score lower. What does that mean in terms of your grade? Well, first thing that you need to know is that you're not going to get a grade out of 70 and that percentage be your grade for the exam. That's not going to happen. And it's a good thing that's not going to happen, because that would mean that most of you would end up failing. Because to do average, 40 out of 70, that's about a 60%. Not so great. On our scale, that's a D. So we're not going to hold you to that standard. If the average student gets a D on this test, we're not going to say, okay, well, that's your grade too. Good luck. See you next semester. No, we're not going to do that. We're going to use this to kind of set our bar. So I can't tell you exactly what it's going to look like, but generally speaking, we have used the median to reflect somewhere in the B range what a B looks like. So maybe it's 82%, and that's what we set it at. Maybe it's 85%. We set it there. It changes semester by semester because the way that we teach changes slightly from semester to semester, and the group of students changes by semester as well. So it's not a uniform, okay, well, we're going to grade this out of 56, and then scale it to 150 points or whatever the number is. What I can tell you is that historically, if you score at the median, you can expect to get a B on the exam. You score above it, you start shading your way up toward A. You score below it, you start shading your way towards C, D, and so on. So the aim for you tomorrow is not about trying to max out the scale. We've been giving versions of the ACS exam here for several years. We've never had someone get a perfect score. And that's okay. That's okay. Perfectly okay. We've had people score in the 60s. We've had people score in the 50s. What you need to worry about is doing your best. And more importantly, you need to worry about trying to do better than your worst day this semester. Because if you think about how your grade is calculated, if you're looking to stay where you are, then you need to basically hit your exam average. So if you've been averaging a B, you need to get a B on the exam tomorrow. Keep your grade. If you want to elevate it, you got to do a little bit better. So what you need to think about is, how do I raise my average? Well, how do you raise your average? You take your lowest score and you beat it. That raises your average. So think about that worst exam that you had, whatever was going on. Do you think you can do better than that day? That's kind of what you're shooting for. You're going for your best. You know, doing your best shouldn't be something that is difficult to strive for. It should be attainable. But that also means that you've got to do the work to make sure that you're at your optimal performance tomorrow. And we've got a tight spot. 6 p.m. final is no joke. It's right up there with 8 a.m. final. 8 a.m. you're groggy because you just rolled out of bed and you don't necessarily have all of your wherewithals. 6 p.m. it's the end of the day. Hopefully you ate something before the exam. But you're kind of tired. You're kind of going the other direction. So self-care in these next 36 hours is critical. That means you got to go to bed relatively good time tonight. You don't want to stay up way too late. Also means that sometime during the day tomorrow, you're going to want to take a break for yourself, at least one. Tomorrow we're having an open session over in the next room from 2 to 4. Reason I stopped that session at 4 is exactly for that. Give yourself a break. That 2-hour time window between the end of that session and the final exam, you shouldn't be doing very much studying. You should find a place to rest or go get something to eat, get away from it for half an hour, 45 minutes, so that you're charged up and ready to go. So it's all the little things, not just what the words on the page are about. Take care of yourselves tonight. That's going to go a long way to making tomorrow a better day. So, any questions about the exam kind of format or grading scale, any of that kind of stuff before I start taking your questions? Good.
So it's not worth like a certain percentage, it just goes for a category?
Yes. Yes, so in my class, the final exam is worth 150 points. And so if you scale that next to your other exams have averaged about 80 points each. So it's a little bit less than 2 exams, if you want to think about it that way. So still important, still going to have an impact on your grade, but No, it does not get its own line item. So in a lot of ways that works out to your benefit, because you can kind of lean on those other exams. If you did well on the other 3 exams, you don't have to do nearly as well on the final, because they kind of will buffer your average. But like I said, you should be shooting for doing better than your worst exam. If you can do better than your worst exam, you're going to at minimum keep the grade that you have right now. Right. Any other questions?
When should we expect like the grade to be in?
So because the exam is a Scantron exam, because it's a Scantron exam, we will probably have it graded that evening. But we usually meet the morning after, because by the time the exam is over and we've graded and everything, it's well after 8 o'clock and we just want to go home, see our families, and get rest ourselves. So we usually meet sometime the next morning to talk about how to scale and how to calculate the final raw grades. So I would expect that by noon on Thursday, you'll probably have some kind of an inkling, and since that's the last grade that is in the book, that'll also be, you should have a pretty good expectation that whatever shows up as that expected grade, that would also be the grade that gets recorded. All right, other questions? Otherwise, we will get started. All right, let's get into it then. Like all my review sessions, I'm going to ask you what you want to talk about. So let's get into your questions here. Okay.
Can we do number 3 on the thermochemistry?
Sure. All right. So we're looking at number 3 here. All right. How much energy is released by the reaction during the formation of 140 grams of nitrogen? Okay, this was a very common kind of question that we saw on the Thermochem quiz as well as on that third exam. So here's this following. That's not. So what we need to do is, this is basically a stoichiometry kind of problem. We need to take those 140 grams of nitrogen and turn them into moles, and then turn that into energy. All right, so take a second and try to scheme that out. And we'll go over it in a minute. One thing that should be noted about these kinds of exams is that it is often done in such a way that we can, usually the math works out very cleanly. And what I mean by that is, when we find that we're using molar masses like these, a lot of times the molar masses are going to be common multiples of the mass given. So nitrogen itself, if you have a periodic table in front of you, nitrogen's 14 grams per mole. Since there are 2 of them, it would be 28 grams per mole. And so our first step would be to take those 140 grams and convert them into moles. And then the second step would be we need to turn the moles of nitrogen into kilojoules. This is where the balanced chemical equation comes in. Balanced equation says I have 3 nitrogens for every 1,078 kilojoules. So 140 times 1078 divided by 28 divided by 3 gives me 1,797 kilojoules. Now, based off of the sign, it's negative. It asks us how much energy is released, so we're okay with the positive value there. The answer would be B. So this was a question that I know a lot of you got tripped up on, both on the exam and in the quiz. Thermochemistry was probably one of our hardest units, just in general, based on quiz and exam performance. All right, any questions with this? All right, we're going to bounce around then. Had a request to look at 2 of the questions in the final packet. So we're going to look at those. All right, so question number 46 was the first one mentioned. All right, question 46 is it's a tough question. This is a limiting reactant kind of problem. So ordinarily, when we have limiting reactant kinds of problems like this, we usually figure out what the limiting reactant is by converting to a common product and seeing which one makes less. In this particular instance, we could do that, but it'd be a whole lot of extra work to do so, because that's not what the question's asking. It's not asking us what the yield is. It's asking us what the limiting reactant is and how much of it is left over at the end of the process. So what we need to do is we need to figure out how many moles of each of these things there are, and from there, we might be able to eliminate some options just based upon what the result is. So starting with our 3 grams of C3H8O. So we'll do this one up here. Molar mass of carbon is 12. Molar mass of hydrogen is 1. So 12 times 3 plus 8 times 1 plus 16 is 60. Now, one thing you'll notice, I've been hammering you all year long on significant figures. On an exam like this, unless there are distinct differences that are based in rounding, you don't need to be nearly as heavy-handed with significant figures because you're choosing a multiple choice answer anyway. The only thing that you want to be careful of is that you don't over-round and make a mistake because you rounded to 1 sig fig in a beginning step and it made the answer off track compared to what it was. But for things like this, ordinarily I'd have you take that out to 2 decimal places, 60.11. Not going to make a big enough difference here to notice. So we can save ourselves a little bit of time that way. And like I said, look how nicely and neatly the number works out. 3 into 60 is 1/20th, 0.05. On the other hand, 7.38 grams of oxygen. Oxygen's 32 grams per mole. 7.38 divided by 32. This one's not as neat and tidy. .231 moles of oxygen there. Okay, so off of this right here, we can eliminate answer C, we can eliminate answer D. Why can we eliminate those 2 answers? Well, simple. It's more than we started with. It's more than we started with. I can't have that amount to start with, have it participate in a chemical reaction, and somehow end up with more than I began with at the end. That's not how chemical reactions work. So I can eliminate C and D based off of that and that alone. Now, do I know between A and B what I'm looking at, what I'm looking for? Not yet. I need to take it one step further. I need to convert my moles of one of these into moles of the other and see, comparatively which one there's more of. So since I'm right here, 9 moles of oxygen for 2 moles of C3H8O 0.231 times 2 divided by 9 gives me 0.051 moles of and so now we need to recognize, okay, this is a problem as well. This is a problem as well because, look, this is more than what I have. Can't do it. So that means that the oxygen isn't going to all react because it requires more of the C3H8O than what is present, what is available. So with this information, we know that this is our limiting reactant and this is our excess reactant. So based on that logic alone, we can choose letter A. If we did not have that intuition at our fingertips, we could certainly go the other direction here. 0.05 times 9 over 2 gives us 0.225. So this is how much I have, this is how much I use. The leftovers would be the difference between the two. So I could get the 0.006 that way. So one of the things that always comes out in these multiple choice kinds of tests is you can use deductive reasoning and eliminate options that don't make sense. And there are usually, for calculation questions, there are usually at least one, if not two, of the options that usually can be reduced out because when you start to think about them logically, you can't get to that answer ever. You know, we did that with C and D. I calculated the moles of each of them. There was no way I could get to those numbers. So I had to eliminate them as options. And even if I didn't know how to do the next step, choosing between A and B, it's a coin flip. You can do a lot worse than coin flips on a multiple choice exam. All right, any questions with 46? All right, another request came in for number 26. So number 26 talks about the use of a different substance as a replacement for a ozone depleting fire extinguisher in CBRF3. The question is, what is the most probable product if a molecule of this new substance is bombarded with high energy photons like the ones that you would see in the upper atmosphere? And the question is based on these bond energies. So a carbon to carbon single bond is 346, a carbon to chlorine single bond is 327, a carbon to fluorine single bond is 485, carbon to hydrogen bond is 441. Now, sometimes it helps in a question like this just to draw the structure itself, just so that you can see it laid out on paper to know what it's talking about. So I've got a 2-carbon molecule here. One of the carbons has 3 fluorines on it. The other carbon has a hydrogen, a chlorine, and a fluorine. That's the compound that we're looking at. And what we're investigating is which of these bonds is the most likely to break. Is it a bond like this, 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 or this? Now this question sounds really complicated. This is one of the ones that kind of separates the people who score at the top of the scale from those who score in the middle. But if you think it through, this isn't actually as complicated of a question as it sounds. It sounds super complicated because it's talking about bonds breaking and stratospheric ozone. There's a whole lot of fluff in here. The question is, which of those bonds is the most likely to break? Yeah, the chlorine bond. Why the chlorine bond, Isaac?
Because it has the lowest bond energy.
Yeah, it has the smallest energy, so it's the easiest to break. So when I break this bond, what am I going to have left? I'm going to have a chlorine atom, and I'm going to have this mess. Which one of those answers represents that? It's C. So like I said, sometimes questions are written to be deliberately obtuse. Try to confuse you with a whole bunch of extra information and kind of get your eye off the ball. But if you can kind of figure out what the question is ultimately asking, sometimes those questions are actually the easiest ones on the test. Because they're using a whole bunch of language to try to confuse the point. And the point's actually pretty simple usually. Right. Other questions off of any of these? Okay. 15, 1-5. Right. So this one, okay. To answer a question like 15, we have to go back to quantum numbers. Now, the question here isn't about quantum numbers, but you'll understand my point here in a second. If you remember the 4 quantum numbers, the 4 quantum numbers gave us different levels of specificity on where an electron was. We went from the energy level to the sublevel to the orbital to the electron. Well, the sublevel isn't being described here, it's the orbital itself. We're talking about the dxy orbital. Now, they could honestly put any orbital in that spot. The answer's going to be the same regardless. How many electrons can fit into any orbital? 2. 1 up and 1 down. So it doesn't matter if it's dxy or dx squared minus y squared or f xyz. It doesn't matter. If it's an orbital, it holds 2 electrons. Right, more questions? Okay, go ahead.
Could you go over the differences between the properties that do require like certain mass and don't? Like mass affects these properties, doesn't affect these properties. I don't remember
Okay.
what they're called.
Okay. Are we talking about intensive properties versus extensive?
Maybe.
Okay. Right. So an intensive property is one that is going to be the same and measured the same regardless of how much stuff there is. So for example, if I'm measuring the air temperature, it doesn't matter if I'm in a confined space like a beaker or in the atmosphere of this room or even outside. A thermometer is going to be able to do the job because the thermal property of air is dependent upon the energy of the molecules, not on how many molecules there are. Other examples are things like melting point. Ice melts at 0 degrees Celsius. It doesn't matter if I have an iceberg's worth of ice or a ice nugget from a convenience store. They're both going to melt at the same temperature. Extensive properties, on the other hand, are properties that are related to how much stuff there is. So, for example, volume. The volume of a large container of water is going to be different from the volume of a small container of water. They have different amounts of matter in each of them. Mass is another example of an extensive property. The more stuff there is, the more massive it's going to be. And things like heat, enthalpy, those are extensive properties as well. Because think about it this way, if I'm going to build a bonfire, the amount of wood that I have on the fire is going to make a big difference in terms of how much heat it generates. If I set up a couple of little matchsticks and a bunch of Lincoln logs, it's not going to generate very much heat. But if I fell a large tree and burned the wood off of that tree, it's going to give off a considerable amount of heat by comparison. And so, different properties kind of weigh in there. So that the question that we did a couple of examples ago, that's an example of that extensive kind of nature of energy, where we were looking at, what was it, 20 grams or whatever of nitrogen. Well, if that 20 grams was 50 grams or 100 grams, the heat value would be different in each of those cases. So I'm not sure if that was exactly what you're asking, but it sounded the most like. Go ahead, Maka.
Can you explain 24 on the exam review?
Yeah. All right, 24. Sulfur dioxide can be described by the structures shown. So what do we call the structures that are shown here in number 24? I've got two different depictions of the same molecule. Yeah, this is resonance. So what does resonance indicate? So we look at each of these individual. The first one, the bonds in sulfur dioxide are of equal length, and the electronic distribution in the two sulfur to oxygen bonds is identical. That is the definition of resonance. So the example we gave was ozone. We also gave examples of like carbonate and nitrate ions. The idea that that double bond is in motion. We talked about this when we talked about bond length. If I look at the bond length of this sulfur to oxygen bond here, it is the same as this sulfur to oxygen bond there. We wouldn't expect that if it was truly a double bond and a single bond. We know that double bonds are shorter than single bonds. But the fact that they're the same indicates that what we have there is delocalization. We've got that electron group that is moving around from one side to the other. And so, if we look at each of the ones after this individually, we can start to pinpoint why they're wrong in that context. So letter B, the single bond being longer than the double bond, the electronic distribution being different. That would be the case if this wasn't resonance. If there was no resonance there, that's exactly what we would expect to see. But if there was no resonance there, we would have no need to show both structures. We would just say, okay, there's a double bond on this side and a single bond on this side, and that's what the molecule is. But we don't say that. We show both structures because they're both identical because of that delocalization. Letter C, the electron pair in the sulfur dioxide molecule alternates back and forth between the two sulfur oxygen electron pairs so that the different bonds seem to exchange positions. Okay? That's not true either. Because what that is saying is that the electrons are literally moving. They are hopping. So this electron pair goes down and makes this double bond, and this double bond scoops up to replace that electron pair. So that's how I get from this one to this one. But that's not what happens either. Because again, if we saw that, we would be able to track that kind of movement of electrons. Well, letter D, the sulfur dioxide molecule revolves. And so the electron to the sulfur to oxygen bonds seem to exchange positions. Well, that'd be really easy to figure out as well. Because if all that the molecule is doing is rotating, well, that means that it's still a double bond on one side and a single bond on the other. Spectroscopically, I'd be able to measure a double bond and a single bond when I'm evaluating bond lengths. So that one doesn't make any sense either. So A is the only correct answer here, and that is the literal definition of what resonance is. What resonance tells us is that it's not that the electrons are moving around, and pair hopping and swapping. What's happening is that this set of electrons here that makes this double bond is not fixed in one position, but rather moving between all three atoms at the same time. So this lone pair doesn't move. These lone pairs don't move. that remaining couple of electrons gets stabilized between these three atoms. That's what resonance is. And that's why when we measure bond length in a resonance structure, we get the same length for all of the involved bonds. Because they have to be identical to each other electronically, not just on paper. Go ahead, Max.
Number 10 on the thermochemistry.
Okay. All right, let's hop back to thermo. Looking at number 10. So what we have to remember, this is a bomb calorimeter. We didn't do a whole lot of calculating with bomb calorimeters because we don't have access to use them very often. But what we understand is that the heat from a bomb calorimeter is equal to the calorimetry constant times the change in temperature. And so if we remember that detail, the bits and pieces here will kind of start to spill from themselves a little bit. So to find enthalpy, I need to take the calorimeter constant and multiply it by our change in temperature. Our change in temperature, 15 degrees Celsius. So if I do that calculation, I get 18.9 kilojoules. So that's how much energy has to go into the calorimeter to raise its temperature 15 degrees. The question is, how much benzene does it take to do that? Well, I've got a nice conversion here to help me out with that. It says that for every 41.9 kilojoules of energy, 1 gram need to be burned. So if I take that 18.9 and divide by 41.9, I get my 0.45 grams. So this is one of the ones where if you don't know exactly how to go about doing it, there might be enough breadcrumbs in the problem itself that you can kind of connect the dots. So you can look at that and say, okay, well, the calorimeter constant gives me a heat value per degree Celsius. Well, I've got degrees Celsius in the problem, so if I multiply those together, I get an amount of energy. And then I look at the first value there and say, okay, well, that's energy per gram. I need grams. If I can get an energy amount, maybe I can figure out how much mass it's going to require to do it. So this is one where, like, even if you didn't know that equation, they left you enough information in the problem itself that you can kind of see how to link it together. other questions here? Go ahead, Jerry.
Number 67.
Okay, 67. All right, which statement about this redox reaction is correct? Oxygen acts as the oxidant. Peroxide acts as the reducing agent. Peroxide acts as the oxidizing agent, or only oxidation takes place. Okay, based on what we know about oxidation reduction reactions or redox, we know automatically letter D is nonsense. You can't have oxidation without reduction. If something is stealing electrons from another thing, which is what oxidation is, those electrons have to have a place to go. So something's getting reduced along the way. So you can't have oxidation without reduction. It just doesn't work. Those electrons have to be accounted for. So right away we can eliminate letter D. Now the other thing that we can eliminate is we can eliminate letter A. Oxygen acting as an oxidant in this reaction. Well, oxidant is another way of saying oxidizing agent. Where do we find oxidizing agents in redox reactions? Yeah, we find them in the reactants. Oxygen is a product. Not going to work. So we're down to, again, justify logic, we're down to 2. And they are related to what is going on with the peroxide. Now, to understand what's going on with the peroxide, we need to assign oxidation numbers. And this is where it can be a little bit tricky for us because we're not usually doing this kind of oxygen does not usually behave this way. This is one of those weird exceptions. So knowing what we know about hydrogen. Hydrogen is +1 with nonmetals, -1 with metals. And 0 when it's by itself, which doesn't apply here. So if the hydrogen's +1 and I have 2 of them, that means I've got a total of +2 in this molecule, which means I need a total of -2 from the oxygen. Ordinarily, that would mean that we just have 1 oxygen atom. But in this case, we have 2, which means that we have a -1 charge on the oxygen instead of a -2 charge. On the product side, we've got more of the same here, but we also have a 0 for this oxygen. So I've got oxygen going from the -1 state to the 0 state. Our oxidation number is getting bigger, more positive. The name of that process would be oxidation. So here's an instance where I've got an oxygen that is being oxidized, which means that the peroxide, by definition, is the reducing agent. Now, if you carry this all the way through, and so one approach that you could do would be assign oxidation numbers to everything and figure out where the electrons are going. If you did that, you would see that you have a positive 7 on the manganese. That's going to a positive 2 here. And you got a negative 2 on the oxygen here. That is either going to 0 or negative 1, depending upon what product it's going to. At any rate, we can see that the manganese is going from a high oxidation state to a lower one. So its oxidation number is getting smaller, it's getting more negative, which means it's being reduced. So permanganate is the oxidizing agent here. All right, more questions, further questions. Jack?
62.
62?
Yeah.
Right. 62, 62 we may or may not see. This kind of falls into one of those gray areas between Chem 1 and Chem 2. This is just a definition kind of question. So the solubility of a substance, that would be the maximum amount of solute you can dissolve in a given amount of water. And so the solubility for a substance is 60 grams per 100 milliliters at 15 Celsius. We take the solution of this substance that is at its limit, which is called saturated. So when we are at the solubility limit, the name for that solution is saturated, meaning it can't take on any more. Well, the problem describes a scenario where if we increase the temperature, for most things, when we increase the temperature of something, the solubility goes up. Easy example of this is if you're making sweet tea at home. It's a lot easier to dissolve the sugar into the tea when you first brew it than if you try to do it after it's sat in the refrigerator for an hour. Why? Solubility, saturation. The warmer tea is going to be easier to dissolve in because it has a greater capacity for dissolving. And so as you stir it into the hot liquid, it dissolves more quickly. And so long as you don't exceed the saturation limit, when it cools down to the proper temperature, it'll stay dissolved. No. So we do this. We increase the temperature, we dissolve more stuff in it. And then we cool it down slowly back to 15 degrees. And none of the solids separates out. So the solubility limit is 60 grams per 100. We now have 75 grams in that 100 milliliters. 60 being the solubility limit, again, we call that saturated. Anything above that would be something called supersaturated. Now, supersaturated solutions are unstable. So usually what happens is while it might maintain that solubility for a while, little bits of dust, just simply agitating it, shaking it, stirring it, will cause the extra stuff to start to fall out and re-separate. But that's the definition of supersaturation, is if we exceed the solubility limit and it maintains that excess of solubility, even though it's at a temperature where it shouldn't do that, that's supersaturation. So the answer there is B. It wasn't supersaturated at 75. It was supersaturated once we brought it down to where the concentration was above the limit. All right, any further questions? Anything else we want to talk about? Good.
Could you go over the periodic trends and stuff? Because I know some are like weird. Remember.
Okay. All right, so when it comes to periodic trends, if we're talking about like physical property trends, there are three primary trends that we want to look at. The first is size, and that one's pretty straightforward. As you go down the periodic table, we are going to see that the atoms get bigger. And the primary reason there is real simple: energy levels. Each successive row of the periodic table represents a new energy level. More energy levels that you have, the further those electrons are going to get from that nucleus, the overall atom's going to get bigger. As you go across, so as you're going from left to right, from the alkali metals to the noble gases, we are going to see that the general trend is decreasing. Atoms are getting smaller. Now, why is that? Well, kind of similar reasoning to what we saw with the first set of reasons. Energy levels, again, play a pretty important role. As we're going across the row, we're not increasing at all in energy level. The energy level is fixed. So the outer bounds are kind of fixed as well. What about the inner bounds? As we go from alkali metal to alkaline earth to transition metal and so on, the boundary of the electrons isn't getting any bigger, but the nucleus is. And that extra nuclear charge coming from each new proton is going to create extra attraction between those electrons and the nucleus. Greater attraction means that they're going to be drawn closer together. So that trend is very straightforward. Going down, we get bigger. Going across, we get smaller. The other big trend that comes up is size. And here's where we have a couple of bumps along the way. For the most part, size is basically, keep saying size, I mean ionization energy. Ionization energy. How much energy does it take to remove an electron from that atom? And generally speaking, it's an inverse relationship to size. The bigger the atom is, the less tightly they're held by the nucleus, the easier it is to pluck off one of those electrons and take it away. And that generally holds. You go up and down the column, more energy levels, easier to get that electron because it's further away. As you go across, kind of the same idea. The atoms are getting smaller, they're being held more tightly by the nucleus, it's a little bit harder to pull them out. Where the exceptions come in is when we start getting into the nitty-gritties of the sublevels. So thus far we've been able to focus kind of on the broad energy level perspective. When we get into the sublevel perspective, we have to start thinking about electron configurations. And there are a couple of electron configurations that have slightly more stability than others. And in particular, when you look for electron configurations where we have a sublevel that is either full or half full. Because full sublevels are going to be more stable. Half full sublevels are going to have a certain extra amount of stability compared to unfilled sublevels. And so where those exceptions start to apply is if I'm looking at group 2 versus group 13. In group 2, my configuration is going to be NS2, NP0, where N is just whatever energy level we're in at that particular time. In group 13, it's going to be NS2, NP1. Why does this make a difference? Well, energetically, the electron I have to remove is going to come from this sublevel. This sublevel is full. This sublevel is stable because it is full. And so because of that stability, it's going to be a little bit harder than we expect to take an electron from it. Just like it's a little bit harder than we'd expect to take an electron from a noble gas. It's full. It doesn't want to get rid of it. By contrast, the group 13 is getting rid of that electron, the one and only electron in that p sublevel. That one and only electron in that p sublevel doesn't have a whole lot else going for it. So it's a little bit easier to remove than maybe we would expect. And as a result of that slight variance in energy, one being a little bit harder to remove, one being a little bit easier to remove, they switched places in the trend. So it's actually easier to remove a group 13 elements electron than a group 2 elements electron. And we can see similar kind of logic in group 15 and group 16. Now for those, I'm going to show you the line notation. Logically speaking, very similar. I've got to take away an electron from a half-filled sublet. Instead of taking one away from an orbital where there's already a little bit of repulsion there, and so it's a little bit easier to remove. And so as a result, 15 and 16, they switch places as well in that trend. And so those are the two biggest trends that we look at as far as periodic trends are concerned. Now, there are other things that might come up in the name of periodic trends. You might be asked to look at things from an ionic size standpoint, or maybe you're looking at a whole bunch of things that have the same number of electrons and trying to figure out which one's the biggest. Well, in those cases, what you really want to think about is attraction. So if I have a whole bunch of things that have 18 electrons in them, so just by example here, let's say I had the sulfide ion, the chloride ion, argon, potassium ion, and calcium ion. Well, all 5 of these have 18 electrons in them. They all have the exact same electron configuration. How do I know which one's bigger and which one's smaller? Attraction. While they all have the same number of electrons, they don't all have the same number of protons. Calcium ion, because it has the most protons, is going to have the greatest attraction. And because of that greatest attraction, it's going to be the smallest. The sulfide ion with the fewest protons is going to have the least attraction. And it would be the largest as a result. Right. Anything else we want to talk about? Starting to look a little worn, so unless we have something specific that we want to go through, I'm content to let you walk out when you're ready. All right, so if you've got other questions, you've got things that come up, feel free to reach out to me. Be glad to help you out. I'll be on Remind. I'll be on Blackboard Message as well. So feel free to reach out to me any way that you want. Make sure that you take care of yourselves this evening. Make a definite plan for tomorrow. I don't know what your other schedules are. I don't know how many tests you have tomorrow, but strategize and think about how can I be my best self tomorrow at 6. So get some sleep tonight. Make sure that you build in a good solid break time. You don't want to be cramming all the way up till the minute of the exam. You gotta have something left in the tank by the time we get to 6 o'clock. If you have any questions you want to hang around, feel free to do so. Otherwise, thank you for coming out, and I'll see you tomorrow.